My final presentation is on the four-color theorem. The four-color theorem came about in 1850 when Francis Guthrie discovered he could color a map of England's counties using only four colors, and in which two counties with a common boundary line had different colors. He then tried to prove that regions on any map could be four-colored, but he wasn't satisfied with his proof and shared it with his brother, who shared it with his professors, and word of the problem began to spread. In 1879, the first published proof attempt was written by A.V. Kemp. Now we look at an outline of Kemp's proof. Any map on the plane is represented as follows. In each region, we place a vertex. If two regions share a common boundary line, we use an edge to connect the vertices for those regions. An important theorem to note is any maximal plane graph G with at least 5 vertices has a vertex V of degree 3, 4, or 5. Assume the four-color theorem is false and let G be a maximal plane graph with the fewest vertices, which is not four-colorable. According to the theorem above, we have three cases. Case 1, degree V equals 3. The vertices of G adjacent to V use only 3 of the 4 colors used on G minus V, leaving the fourth color available for V. This is a contradiction. In case 2, we have degree V equals 4. If only 3 colors are used on the adjacencies of V, then we use the fourth color on V. If not, assume the neighbors of V are clockwise V1, V2, V3, V4, and are colored 1, 2, 3, 4, respectively. Interchange colors on all points colored 1 and 3, which can be reached by a 1-3 chain from V1. Now we see that V1 and V3 are colored 3, and now V can be colored 1. This is also a contradiction. In case 3, we have degree V equals 5. Let the vertices adjacent to V be clockwise V1, V2, V3, V4, and V5 be colored 1, 2, 1, 3, and 4, respectively. If there exists no 2 to 4 chain from V2 to V5, we can interchange colors on all vertices that can be reached from V2. Now V2 and V5 are colored 4, and V can be colored 2. In Haywood's counterexample, he shows that after interchanging colors on the 1-3 chain from V1, the 1-4 chain from V3 connects to V5. Thus, interchanging colors on the 1-4 chain leaves V5 colored 1 and V3 colored 4. We can see this by coloring V1 3 and changing all the connecting vertices that are colored 1 and 3. Now we change V3 to 4, and this changes all the connecting vertices. And now we see that V5 is colored 1, V3 is colored 4, and there's no color left for V. Although Haywood's counterexample could be four-colorable, he used it to show that Kemp's proof did not always work. Important vocabulary for Apel and Hagen's proof. A graph H is reducible if H cannot be contained in G. H1 consists of a vertex of degree 3 and H2 consists of a vertex of degree 4. Kemp was able to prove these graphs were reducible as shown in the previous slides. A set S of graphs is unavoidable if each maximal plane graph with at least 5 vertices must contain at least one element of S. In proving the four-color theorem, the idea was to find an unavoidable set of S and show that each element of S is reducible. Now we look at Apel and Hagen's proof. Before Apel and Hagen's proof, mathematicians were able to show that every plane graph with at most 96 vertices can be four-colored. Apel and Hagen were able to find an unavoidable set with about 1,500 elements. The steps used to prove their theorem were to get a set of unavoidable configurations using a complicated discharging procedure, show that all of the configurations are reducible using the computer, continue using the program until finding a configuration K for which reducibility was not verified after 30 minutes of computer time, and then modifying the discharging procedure to generate an unavoidable set which does not include K. Using these steps, they were able to complete the proof. This is considered such a remarkable proof because it's considered the first proof of a major theorem that made extensive use of the computer and probably would not have been completed without one. Thank you.